The Advanced Cryogenic Evolved Stage is a new, larger upper stage that would fly on the Vulcan rocket. ACES has a combination of attributes. One is it's a much bigger stage. It has 3 times the propellant capacity of the Centaur, about 4 times the thrust of the Centaur. So it's a much larger stage. It's a much more optimal stage for the upcoming Vulcan booster. ACES has a number of elements to it that are really key technologies. One of those, and really the most important, is the Integrated Vehicle Fluids Propulsion Subsystem. This is essentially an APU, an auxiliary power unit, that burns hydrogen and oxygen out of the tanks. It makes electricity, and that actually gets rid of all our main vehicle batteries. It also autogenously pressurizes the tanks, and that eliminates what we've historically used, which is helium. Third thing it does is it offers an attitude control system capability. So what it does is it has small thrusters that basically do the attitude control. The second key technology is next generation avionics. In next generation avionics, we're going after extra modularity in the system and significantly lower recurring costs. The next key feature are the engines. We have set some aggressive cost objectives to get our engines for the ACES less expensive than today. Some of those engine options include an RL-10 derivative from Aerojet Rocketdyne, an X-Core option, and a Blue Origin option derived from the BE-3. So we are heading toward a competitive engine downselect environment where we actually are trading various options to be the ACES engine option. So ACES fundamentally has 3 key features to it. One is it's a much higher performing stage. With Vulcan ACES, the combination, and the maximum number of solids on the Vulcan, we will have on the order at least 20% more payload performance than the current Delta IV Heavy. Also, that big increase in performance could be of value to customers to actually have more maximum performance. The next key feature of the stage is really inexpensive. So we're targeting the ACES stage to be the same or less cost than today's Centaur, which is a much physically smaller stage. We're looking at some new ways of doing welding and joining and inspection of the welds and such that we think we can get considerable cost out of the structure manufacturer. And then the last one is mission flexibility. ACES, with using its IVF subsystem, essentially has constraints on duration largely removed. Our current mission durations are hours. Today we could go to days, and with growth options even into weeks and months on orbit. And so we do much longer missions with more burns. We can provide a significant amount of electrical power to payloads with the same propellant load because we have this long duration and low boil off as well. So the design philosophy of ACES is really trying to take advantage of the best of Atlas and the best of Delta. We're trying to take advantage of the best of each. So the structure of ACES uses a construction method very similar to the Centaur, which has really exceptional mass fraction to it. Delta, for example, uses aft avionics versus forward avionics that simplifies operations, means you don't have to have a clean room for processing, for example. And so we're trying to amalgamate the best parts of each of our heritages together in the ACES stage. Our planning right now is for ACES to be fielded in 2023. When ACES comes along, it's really a game changer in terms of a big increase in performance and really some very significant cost savings that come along with that as well.